Okay, is it in presentation mode?
No, if you can put it in full screen mode, please, that would help.
Yeah. Uh, Let me try.
Marcus, maybe you can try to share again because I think probably you have it in the other screen,
Yeah.
the presentation mode. We still don't see it in the presentation mode. No, now.
Yeah,
that's working.
better.
Okay,
Yeah.
sorry for the delay.
Right, off you go then. Great, thank you.
Yes, so thank you very much for having me here. So my name is Marcus Ulias, and I work together with my colleagues Ilhan and Nulia, who are also today in this meeting at Sperum AB in Sweden. And yeah, we will be discussing and showing the results of a project that had a look at the effect of vanadium carbides on hydrogen embrittlement resistance in spot welded, cold formed, high strength steels for automotive applications. So that means, for example, body in white applications. And this was in cooperation with Vanitech and SSAB. Yes, so coming to the background, we have all heard that advanced high-strength steels, they're really useful for automotive applications because they reduce the weight in body-in-white applications. But due to their high strength, there is always a risk for hydrogen embrittlement. And in this project, we would like to investigate a bit more what happens with the microstructure and hydrogen embrittlement sensitivity of the spot welded cold formed steels for those automotive applications when we add different percentages of vanadium to them. The main questions that we had are, can additions of 0.15 and 0.30 weight percent of vanadium reduce the risk for hydrogen embrittlement compared to reference material with no vanadium added when it comes to these automotive steels. Another question was to find out how to, or to see how spot welding influences the efficiency of vanadium on the hydrogen embrittlement resistance, and also to investigate the effect of electrogalvanizing that is done before spot welding on the efficiency of vanadium on the hydrogen embrittlement resistance. This is how the project plan looks like. And as you can see on top, the end date that is selected here is March 2024. And this is because the project will be prolonged for a few months. We talked to David about that. And it will probably not be taking all the time until March 2024. We will probably end before, but a prolongation for the project was asked for because there are some tests left still. And what we can see here regarding the project plan is that we have two accomplished work packages, work package 1 and 2. One is the manufacturing of the material, and the other one is the processing of the material when it comes to welding and electrogalvanizing the material. Then we also have a third work package that looks at heat affected zone simulations by telemetry and electrometry, sorry. And since we already have quite good characterization by TEM and TTMS of the real welded material, we can skip this work package. Work package 4, microstructure and residual stresses, is partially done. The missing part are the residual stress measurements, and work package 5 is still ongoing. So here we can have a look at the materials that we investigated in the table that you see here. On top, the blue one is the reference material without vanadium, and then we have 0.15 and 0.30 weight percent vanadium added to the other two materials. the strength that was obtained for those materials is about 1700 megapascals. And after production, those materials were processed in Weevil. Here we can have a look at how the electrogalvanizing of the samples happened. So there was a pickling to remove the oxides. And yeah, in the bottom, you can see the sample that is a bit shinier than the one on top. That's how it looks like after electrogalvanizing. Then when it comes to spot welding, we have done a lot of trials to optimize the spot welding parameters. And you can see the final ones in the table here. And what is also worth mentioning is that the sheets that we used for testing, they're quite smaller compared to the ones that are normally used. But still in those very small specimen, we see a difference despite their small size. And in the bottom, you can see two examples of spot welded samples. On the left, you have the uncoated state, and on the right, you have the electro-galvanized coated state. As mentioned, work package 3 is not relevant anymore, but for work package 4, we have characterized 0.15 and 0.30 weight% vanadium material using TEM. But no TEM was done for the reference material because in that, since there is no vanadium, there won't be any vanadium carbide. And here we can have a look at the results. We have the non-welded 0.15 and 0.30 weight% material here. And yeah, the main conclusion that you can take from those results is that you can, or from those images here, is that you can see carbides in both materials, which we will have a closer look at in the next slides. Yeah, so here we see the chemical composition in the carbides, of the carbides in the graph on the top left. And even though the bars are slightly different for B15, which is the 0.15% vanadium, and B30, that's the 0.30% vanadium material. So even though they're slightly different, we cannot finally say that one of them has more or less vanadium than the other, since it cannot be measured that precisely. It could be that there are small changes in the stoichiometry, but it is hard to prove because even APT technique does not, cannot differentiate so well between those two. What we also see here in the table on the right is the particle size distribution connected to those who have the two graphs in the center. And they basically show that the particles that were found are quite similar in size when it comes to those two materials. But what is interesting to see is that the 0.30% material has about twice as many particles than the 0.15% material. So that means the size is approximately the same, but the amount is about twice as much in the material that has about twice as much vanadium. In the images on the bottom, you can also get an impression of how the size distribution looks like in reality. And here we can see the TEM results for the 0.15 weight% material. For this material, TEM analysis was done in the weld and in the heat affected zone. You can see the areas in the top left in this optical microscope image. There, the areas are marked. And for those tests, it was seen that in the weld, the carbides were pretty much dissolved. But in the heat affected zone, there are quite a few small vanadium carbides and a few bigger titanium carbides. So for those, it can be said that the size of the carbides varied quite a lot. here we have the results of the 0.30% material. For those, so far only the results for the center of the weld are obtained yet. The other ones are still to come for the heat affected zone. And here we could state that even in the center of the weld, as opposed to the 0.15% material. So here, even in the center of the weld, some carbides were found, and they could, but this still needs to be proved, influence the time to failure in the constant load tests. And those tests we will have a look at in later slides. So it might be possible that a higher vanadium content could result in carbides surviving the melting during the welding, so that their capability in terms of hydrogen trapping could remain. Yes, so here we can have a look at work package 4 and 5. The microstructure analysis is done, and the XRD analysis of residual stress is in progress. And the goal here is to see if there are residual stresses from spot welding remaining and what effect they would have on the hydrogen embrittlement sensitivity. So here we can see how the hydrogen embrittlement sensitivity was analyzed. We charged the samples according to the procedures in the colored boxes below. So in the green box, we see the procedure for the samples for the step load test. That's some kind of constant load test. And in the blue box on the right, we see the procedure of the samples for the TDMS analysis. So that's the analysis where we measure how many ppm of hydrogen are in the material. And some smaller parts of the evaluation are still ongoing, but we're going to show some results in later slides. Just a comment here in the green box, it says polished edges. We polish the edges because we want to have cracking in the spot weld during the test and not on the edges where different surface roughness might increase the amount of hydrogen there. So here we see the results of the TDMS measurements, thermal desorption melt spectroscopy measurements that measure the hydrogen content in the material. And as a general point regarding the status, the color coding in the top of the text, green and yellow, shows basically which activities are done. Those are the green ones, and the ones in yellow are still ongoing. And in the graphs, you can see the different materials. So for V0, that's the reference material. With 0.15, with 30%. And here we see the dark blue graphs, which show the hydrogen contents measured during.
Excuse me, could I ask everyone to mute their microphones, please?
You can mute them.
Yes, there are some noise in the background. It was difficult to follow you, Marcus.
Oh, sorry.
Sorry, could we ask everyone to mute their microphones, please?
Yeah.
Dave, you can go to and mute them yourself.
When I start the meeting, so I didn't log in, so I'm not the host, so I can't do it.
Okay.
No. Oh.
I think it is. Yeah, now it's been muted. Yeah.
Okay. Thanks.
Okay. Thank you,
Could
Marcus.
you start over, Marcus, please?
Yeah, of course. Sorry.
Thank you.
I will. So here we see the TDMS graphs of the materials with the different vanadium contents. Maybe I can get the pointer. Here, the reference material without vanadium, 0.15%, 0.30%. And for each of them, the hydrogen content was measured directly after charging. This is the dark blue curve for all of them. We see it's the highest. And then we left the samples at air for 1 hour and for 3 hours at room temperature. And after 1 hour, we could see that the hydrogen content has decreased for all of them. That's the yellow curve. And after 3 hours, it has decreased even further. And in the following slide, we summarized those values in numbers that it's a bit easier to see. So here in the graph on the left, we see the gradual decrease of hydrogen when leaving them at air for 0 hours, 1 hour, and 3 hours. And we calculated the loss of this diffusible hydrogen. And the summary of this is on the graph on the right. So to calculate that, we assumed that after charging, so after 0 hours, we had 100% hydrogen. And then we calculated how much was lost after 1 hour. That's the orange graph, which is quite similar for all of the materials, and how much was lost after 3 hours, the gray bars. And here we can actually see that the material that had 0% vanadium lost the most, whereas the 0.15 and 0.30% material, they have not really a significant difference in hydrogen loss. So that means that they could retain the most hydrogen compared, or more hydrogen compared to the reference materials. Here we can have a look at the constant load testing results. If we look at the graphs here, we can see that there is an improvement for the 0.30% material compared to the reference material without any vanadium and the material with 0.15 weight percent. This means, in case you have not seen those graphs so much, so the longer the time to fracture is in those graphs, so the higher the bars, the better does the material perform. Then we can also see that the coated material in most cases lasts for a shorter time than the uncoated material. And this is probably because there is a galvanic reaction between the zinc coating and the steel of the bulk material on the sheared edges. And that reaction can produce hydrogen, which in turn can affect the results of those tests. We can also see that for the spot welded material, the spot welded material performs worse than the non-spot welded material in both coated and uncoated conditions. And this is possibly due to the different size and dissolution of the vanadium carbides in the heat affected zone. And it could also be due to residual stresses from welding. And to better understand this behavior, we will perform fractography analysis on the samples. So here we can summarize the results so far. We have seen that vanadium has a positive effect when it comes to hydrogen embrittlement resistance. And a vanadium content of 0.30 weight% in those alloys had longer times to fracture in the test I just showed as a result compared to the reference material and the 0.15 weight% material. That applies both for the base material and also for the welded joints. When looking at the carbide sizes, we had similar sizes for both materials and about double the number for 0.30% and 0.15%. And this applies mostly for the heat affected zone and only for the 0.30%. A few carbides were found in the actual weld. When we did cathodic charging on the materials, we saw higher diffusible hydrogen uptake in 0.15% material than in 0.30. And that's both for the uncoated and the non-spot welded material. Then we calculated the loss of diffusible hydrogen after 1 hour and 3 hours resting the samples at air. And there was a similar trapping efficiency for the 0.15 and 0.30% materials. We can also state that electrogalvanizing with zinc decrease the resistance to hydrogen embrittlement for all materials and conditions. And finally, we can say that spot welding decreased the hydrogen embrittlement resistance, and that's probably attributed to the dissolution of the carbides in the spot weld and the size of the carbides in the heat affected zone. Then we have the final slide here. So talking about the future work, we plan to finish the constant load testing and to perform fructography on the samples there. And we also would like to perform more TDMS tests on this, especially on the 0.30 weight% material. Then the residual stress measurements will be done. And finally, also the results will be disseminated. Yeah, so thank you very much for your attention. And both me and my colleagues are happy to answer any questions if there are any. Thank you very much.
Thank you very much for that presentation, Marcus. I think we're seeing some positive results there. Are there any questions or comments for Marcus or Nuria on this presentation?
David, Dr. Singh here, Marcus, it's a wonderful work, and this subject is very close to my heart for the last 25 years.
Oh, thank you so much. Thanks. I appreciate it. Thank you very much.
Just to know, actually, when you are charging hydrogen, what kind of electrolyte you have used?
Yes, so we have the electrolytes here. For the step load testing, we use 0.5 molar sodium sulfate with this current density here. For the uncoated material, for the coated material, that's the electrogalvanized material with zinc, we use sodium chloride. And when it comes to the charging prior to TDMS, we used sodium chloride plus a recombination poison. That's diarrhea in this case, 1 gram per liter, with the current densities, as you can see here.
So great, Marcus, since it must have inspired all of you, entire group, and thanks to Ventec for this project. In real life situation in the automotive, you must have noticed by some reports actually from automotive makers that hydrogen embrittlement has occurred actually at the spot welded, correct? Any failure reports came from automotive industry that spot welding is causing some hydrogen embrittlement? I hope so, and that's why this work is going on. This is very interesting, yeah. Did it happen in the real life situation in the automotive?
It's Birkan here, or Nuria, maybe you can comment.
No,
if you want.
can go ahead, please.
Yeah, so nothing that happened that we are aware of so far. It might be happened, but it's confidential and it's under development work. But definitely the idea was that the spot welding itself is introducing stresses, and as we can see from the results, it has effect on the carbides, so it dissolves them. And as we know that vanadium carbides should act as so good traps for diffusible hydrogen. That's the work that we did here with this DDS, this desorption, hydrogen desorption. So we wanted to check actually in this work whether the spot welding is a threat. But in fact, our results indicate that in case, of course, the conditions that we use now are not in-service conditions, it's lab testing conditions. It is strong indication that spot welding might be a possible threat for these high-strength steels, definitely.
As per my experience, because when I was doing for high carbon material having 1,900 MPa strength high carbon steel wires, and we found we were testing at 70% of the tensile strength actually. And we found actually this is happening at very high corrosive. There is a FIP test actually in ammonium thiocyanate, which is highly corrosive when I was charging hydrogen. The reason is in the concrete, these materials were failing after certain years. And when Gamera made 1900 kilometers of concrete pipes for a 75 years life, they started failing in 5 to 7 years time. and the work was given to Imperial College and Swindon Technology Center and National Physical Laboratory, Teddington in the UK. So when the stresses are there, certainly it is going to have a very, very adverse effect on the material. And I hope spot welding is creating some stresses as well, which I noticed actually what happens is that we were using the scanning reference electrode technique for mapping what's going on during the corrosion process and hydrogen charging. And we noticed the pitting over there. And when the pits are formed, this is more causes the problem and failure happened here. So have you noticed after charging any pitting formation on the spot welded area?
I mean, first of all, we have not used any recombination poison for the mechanical degradation test. As you can see in the green box, it's solely electrolyte, which is probably not so corrosive. Of course, it's corrosive, but in the case that we see, for example, for the coated, which is just simply sodium chloride, and then the reaction that we expect there that it will happen that produce hydrogen, it's basically the galvanic effect between the zinc and the shared edges of the metal. And on contrary, on the uncoated, we used sodium sulfide without any recombination poison and very mild current densities that we, from our experience, we know that would charge slowly hydrogen, so no strong effect will be there. Concerning the hydrogen trapping, we use thiourea, and that is also based on some sort of organic thiocyanate. But these results are not into context with the, let's say, good results that we obtained in this work, that 0.3 vanadium addition will shows better mechanical performance. So this is just to accelerate the hydrogen uptake and to see some effect on the carbides, how they perform in the hydrogen trapping capacity. Okay. But very interesting insight. Thank you very much for your insight.
Welcome. No, it's very interesting work actually. And when you presented last year, and then it created a lot of enthusiasm in me that somebody is working on this area after 25 years on this one.
Yeah, and one thing I must say, I mean, the focus here is on vanadium and additions of vanadium, and in particular for the vanadium carbides. And from literature, it's known that the stoichiometry and the coherency could influence the trapping. And we are actually trying to understand the trapping. And the reason why we are following up now and putting more focus on the V30 material, so 0.30% weight percentage of vanadium, it's basically because we want to understand why only 0.15 plus addition resulted in such better performance. And to end up, I mean, vanadium carbides, they are investigated in literature and presented many different studies, but it's very seldom that people show real mechanical tests that you see improvement in the hydrogen embrittlement sensitivity.
Yeah, thanks for the
it's
interesting
very
discussion.
I mean, there vanadium carbide has various compounds. Yeah. It's not only VC. If I remember it, VC7, etc. I mean, there are so many combinations of.
It's a great discussion, guys. It's a great discussion, but in the interest of time, we have to move on to the next presentation. If you want to email me comments, I can continue the discussion and we can carry on online. But I'm very sorry to cut it short, but we're running behind time, so I think we have to move on to the next presentation. So thanks for the comments and thanks for the presentation. So thank you.
Thank you very much. Thanks for the helpful comments. Thank you very much.
So if you could stop sharing your screen, thank you. And I think our next presentation is Kevin. Are you with us, Kevin? You were earlier. Kevin, are you there?
Yes, I am, Dave. I'm just getting my presentation.
Okay.
Can you see that?
No, not yet.
Oh.
Hey, Kevin, before you get started, I just want to point out I've sent to a few of you some questions in the chat room. If you would all please take a look at the chat room. And if you have any requests from me, just respond back to me personally. It's about your contracts and payments, not about, you don't need to respond to everyone. But if you all could please check your chat room, that would be great. Thanks.